Hey everybody, it's 5 o'clock on Thursday, so it's time for some Calc 3. So, before we get started, first question, audio okay? How's it sound? So far so good, that's what I want to hear. Let's hope it continues. Okay, let me know if there's any issues with the audio. Um, I did a couple tests with it before, about 10 minutes ago, and everything seemed to be working fine, but as we noticed, stuff happens. Okay, so last time we talked about partial derivatives and tangent planes. And they're really closely related. You need to be able to do partial derivatives to find tangent planes. So what we're going to do today is, this is actually I think one of the most interesting sections in not just Calc 3, but all of calculus, because we're going to talk about a tool that is actually really easy to find, but is very powerful, and that is the gradient. Okay. All you have to be able to do is find partial derivatives, and you can find the gradient. And we're going to look at a couple uses today, but the gradient will keep popping up the rest of the semester. All right. And for those of you guys who go on in mathematics, you'll see the gradient again. So what I love about it is it's not that hard to find procedurally. So today what we're going to do is I'll introduce it procedurally, and we're going to talk about it conceptually, and then I'm going to have you try some of the worksheet problems to just really hammer home what it is the gradient finds. All right. So let's dive into this sucker. All right. So this is the contour plot of this function right here. This is x squared plus 2y squared. It's basically an elliptical paraboloid. Okay. We're gonna do some stuff with this here in a little bit, and it's going to involve the contour plot. So if you think about last section, we were talking, or a couple sections ago, when we were doing partial derivatives, we wanted to know the rate of change either in the x or the y direction. So if we were looking for f sub x, it was the derivative in the direction of x holding y constant, or vice versa. Well, as you can imagine, at any given point, there's really an infinite amount of directions in which we can find the rate of change. Because, there's more than just the positive x and the positive y. There's here at the 45 in the xy plane. Here, think of that basically a circle around there. We could find the rate of change. We could want to find a rate of change, or a rate of change exists, I should say, in any of those directions, not just in the x or y direction. So that's going to be our goal today. We didn't do this, so don't worry about that part here. But we're going to learn how to do what's called a directional derivative analytically. And what a directional derivative is, it's the derivative in the direction of a given vector. So all we have to do is find the vector in the direction that we want, make it a unit vector, and we'll be able to find the rate of change in that direction. So you can see how this is really building on this idea of vectors. We talked about unit vectors all the way back in module 1. They keep coming up because we want to preserve direction but get rid of magnitude. So I don't want you guys to worry about this part. This is the definition of the directional derivative. We are not going to find it this way. I used to do this because what we would do is I'd use this definition to derive the formulas. We don't have time for that in the live online version of this class, but what I might do, if I can find some time either tomorrow or this weekend, I'll put together a little video of the derivation of this stuff, just so you can see. It's really cool. It uses our right angle trig, and you can then see how the gradient pops out of this idea of a directional derivative. So I'll try and find some time to put together that video. And then, again, that's not something you'd be expected to know or memorize or do on your own, but just for those of you guys who are interested about where some of this stuff comes from. What this does is this gives us the rate of change in the f in the direction of u. And so notice the notation. So, sorry, I should have that already open. So if you think about what we did last time from a note, even just from a notational standpoint, if we wanted the derivative in, say, the x direction, we would do f in the direction of x of xy. So that would have been the derivative of x in the direction of x, a derivative of f, excuse me, in the direction of x holding y constant. This notation here, notice first off that it's a u instead of x or y, and also it has the hat. So this is going to be one way that you recognize that you're being asked for a directional derivative at a point. Sorry, that hat didn't come out so well. Let me clean that up a little. I point that out because, you know, in a homework or a worksheet or exam, you might be asked to find f sub u at AB. You need to be familiar with that notation and say, okay, f subscript, we know that means a partial derivative, but if it's not x, y, or z, if our function has a z in it, or one of the variables of our function, if it's a u or some other given vector, and we'll know it's a vector because it'll have the little arrow or the hat on it, that's how we know that what we're looking for is a directional derivative. Now, we would need to be given the direction that we want it in. So you would be given. So you would be given in the problem. So it'd be find the rate of change of f of xy in the direction of u would be the problem statement. Or find f sub u of AB where u is a vector, okay? So I just want you to be familiar with that notation. Now, again, I'm not going to do the derivation in here because we always have, you know, I want to make sure we have time for you guys to try some of 13.5 worksheet. But if I'll put together one. But in the derivation, the big thing that pops out is the gradient. And the gradient is a vector, all right? It's a very, very specific vector. It's a vector made up of the partials of the function. So last time we talked about finding partial derivatives, f sub x and f sub y. If you are feeling comfortable with that, which again, it's just our old derivative rules, it's just the new part is having to think of the other variables a constant, which takes some practice. But if you can take the partial derivatives of a function, you can find the gradient because all you're doing is taking the partials and putting them in vector format. So for that, that function that I had earlier, right, f of x y equals x squared plus 2y squared. The gradient of f of xy, we can do it in terms of x and y, which is really cool, is the partial with respect to x, which is 2x, and the partial with respect to y, which is 4y. And there's our gradient. That's how quick it is. And now if we want to do the gradient at a point, so the gradient of this guy at maybe 2, 3, we just plug those in for x and y. So 6, 12. Now, as you saw last time, you know, sometimes depending on how complex our function is, our first order partials can be a little messy, might involve a product rule or something, chain rule or some quotient rule. But if you can do your first order partials, you can find the gradient.
Isn't that 4 and 12?
Yeah, it is. Thank you.
Hear me.
Thanks, Adrian. 4 and 12, because we're putting 2 in for x, 3 in for y. Thank you. See, you guys already have it down. All right. So for right now, what I want you to take from this is the gradient is not hard to find. It is just a vector whose components are made up of our partials. That's all. And they go in order. F sub x, f sub y, and then when we go into 3 space, f sub z is our third component. So finding it procedurally is not a big deal. All right. So it's just a vector made up of our partials. And we can actually find vectors for, we can actually find gradients for functions of 3 variables, 4 variables. I'd like to pretend that I was testing you on that one, but I missed that one. So however many variables are in our function, we can find a gradient for it, and the gradient will just have that many, the same number of variables will have the same number of components. All right. So far, that's what I want you to take away is that, all right, this is great. It's easy to find. Now, here is the directional derivative. Okay, I'm not going to, don't worry about the notes too much. Those aren't that big a deal, but the directional derivative right there, you know, so that f sub u that we were talking about at the point AB comes from dotting our gradient, which we just talked about at AB, with the unit vector in the direction that we're trying to find the rate of change. So just as a note, the reason we're using u, it's a unit vector. So if you're given a unit vector, great, we just dot it. If you're not given a unit vector, you have to take that extra step of making it a unit vector, which means just divide by its magnitude. Okay. So again, procedurally, let's just talk procedurally. We'll talk conceptually here in the next slide. What's really cool about this, the gradient is easy to find. We know how to find a unit vector and we know how to do a dot product. So all we're doing is taking stuff we've already done, partial derivatives for the gradient, unit vectors, and dot product, and that gives us the directional derivative. All right. Probably the biggest error I see on this, other than, you know, maybe a math error in calculating your partials, which can happen to any of us, as we saw right here, is people forget to make the vector that we're looking in the direction of or finding the directional derivative in the direction of a unit vector. Okay, so do remember, we want to preserve the direction, get rid of the magnitude. So that's why we want the unit vector. Okay, now let us talk about the properties of this. Okay, so here's our gradient and here's our u, and we're doing, whoops, yes, and we're doing a dot product. All right. This is going to bring our very interesting property out for us. The reason that this is important, now we're almost never going to find the directional derivative this way. We're always going to use this way. I only bring this up because of the cosine of theta. All right. So what we want to figure out is when this directional derivative is going to be at an absolute maximum. Well, cosine is at a maximum when theta is 0. So the directional derivative is at a maximum when the gradient is in the direction of the directional derivative. I'm going to say that again because this is going to be a really important point. Our directional derivative is at a maximum if the gradient is in the same direction as our directional derivative. The reason that's so important is it means that the gradient always, guys, this is an always true thing. The gradient always points in the direction of maximum increase. Pretty much. So if you guys didn't see what Cooper put in the chat, when the slope points towards the top of a mountain, yes, Remember what we said then, we wanted to be moving in a direction that was perpendicular to our level curve to get to that next level curve as quickly as possible. That is the direction the gradient points in. All right. We're going to look at that a little more. This is what's so cool about the gradient. If you know how to find partials, you know how to find the gradient. If you know how to find the gradient, you know how to find a vector that points in the direction of maximum increase at any given point. So we use that. I used the term a couple sections ago, slope of steepest descent. That's what our gradient finds for us. Finds going up the mountain the quickest. What direction? All right. So again, a tool that's very easy to find if we know how to do partials is very powerful. Now here's a couple things to think about. Now it's at a minimum. Now 0 is actually not the minimum, because if theta is pi or 180 degrees, cosine would be negative, and that's when the directional derivative will be at a minimum, which is when it's going 180 degrees in the opposite direction of u. So if the gradient points in the direction of maximum increase, the negative of the gradient points in the direction of maximum decrease. Okay, maximum rate of decrease. So just like the gradient would point in the direction of going up the mountain the fastest, the negative of the gradient, so in other words, changing the sign on all the components, would point in the direction of going down the mountain the quickest. All right. And guys, if you have questions as we go through this, let me know, because these are the big ideas. This is not a long section, because procedurally it's very easy. And it's just getting these concepts down. So you'll hear me say them over and over again a lot. So if we went over those three cases, if theta is 0, then the direction is the same, and that's the maximum rate of change. And the direction of maximum rate of change is given by the direction of our gradient. The maximum rate of change, which is a scalar, so that what speed are we going, is given by the magnitude of the gradient. If we're going 180 degrees or pi radians, then we're going the minimum or the maximum rate of decrease. Now, if they're perpendicular to each other, then we get our directional derivative of 0, because the direction that the unit vector is pointing in is completely perpendicular to the gradient. In other words, it's perpendicular to the maximum rate of change. So our rate of change would be 0. Now, we're going to talk about that geometrically to make that make more sense. But remember, if we're moving in direction of maximum rate of change, we're moving perpendicular to a level curve. Well, if this is perpendicular to the gradient, then it's actually going in the direction of the level curve, or tangent to the level curve, which means we have a rate of change of 0. So all those ideas we talked about with level curves, when we were just talking about them in general, of walking around on a mountain, if we're going in a direction tangent, our height is not increasing. It's got a rate of change of 0. Now we're mathematically proving all those things that we said intuitively. So that's how all those things just come, they come right back. All right, geometric properties. We talked a little bit about these. We're going to take a look at them too. So the direction of the gradient is perpendicular to a contour of f through AB. So let's take a look at what that looks like. So let's put in a contour plot here. So there's our contour plot. Okay. Just wanted to check something. All right, there's our contour plot. Now let's get this into 3D again. Our contour plot's still over here. Now check this out when I add the gradient. Let's have it, yeah, let's have it to be on a point on the surface. So if I put a point on here, and actually probably we'll see this better if we move this in the Y direction. And let's go in a little bit on the X direction. Okay. So I know it can be a little hard to tell, but look at that. Look at our gradient here, and I can move this around. Let's move it to a spot where it's real obvious. See how that's perpendicular to our level curve? We can also see it here on our function. So we're perpendicular to the level curve, and a vector that would be perpendicular to our gradient would be tangent to the level curve. So a lot of really cool interconnectivity with the gradient and the directional derivative. This is pointing in the direction of maximum increase, because if we go around here, we would want to be going in this direction to go up to the next level curve or gain height as quickly as possible. If we start going off to the side here, yeah, we're going up, but we're definitely not going up as quickly, right? The shortest path between 2 points is a straight line. Now, the magnitude of the gradient vector is the maximum rate of change of f at that point. And it's large when the contours are close together, because we'd be going, you know, when the contours are close together, we have a larger change in z value, or this, in this case, the same change in z value for a shorter distance, okay? So if we look at our contour plot, you know, and we can see it in the curve, right? The curve gets steeper and steeper in the surface, I should call it. In the surface, it gets steeper and steeper. So we would expect the rate of change to go up as we get higher on the curve. Well, look at what's happening with our level plot. As we go further out, the level curves get closer together. So if the closer together we see level curves, the greater we would expect the gradient, the magnitude of the gradient to be. Questions at this point? All right, so we're going to talk about these in 3 space, but I'm going to go through this quickly because all of the same properties we just talked about hold. It's just a function of, sorry, not in 3 space, a function of 3 variables. As we've talked about before, we can't plot a function of 3 variables, so I can't do the cool plotting things I can with this one, but all the same properties hold. But now here's what I want you to take home from this part. If you get a question that says, what's the maximum rate of change of this function at point AB, all you have to do is find the gradient and evaluate it at AB. So I want you to start to get those to be the same question. If you're asked about the maximum rate of change, whether it be direction or magnitude, you're being asked for the gradient. If you're asked for the gradient, you're being asked to find the vector that points in the direction of maximum rate of change, whose magnitude is maximum rate of change, all right? And then we saw how we can use the gradient to do a directional derivative. Then that would be where we'd be asked to find a rate of change in some other direction. Yeah, Cooper.
Hey, you cut out a couple times and that. Can you just repeat the part where you said, okay, if you want to find this, you do this. If you want to find this, you do this. Just like the last 30, 25 seconds or so.
Yeah.
If you wouldn't mind.
Sure. Let me make sure. Am I cutting out now, or are you guys hearing me okay?
You're okay now.
Okay. So if you get asked to find the maximum rate of change of a function at a point, or the direction of maximum increase or steepest ascent, you're being asked to find the gradient. If you get asked to find the gradient, you're being asked to find the vector that's in the direction of maximum rate of change and whose magnitude is the maximum rate of change. So again, what I want you to take from this part of our discussion is that those two things mean the same. If you're ever asked for maximum rate of change or maximum rate of decrease, because that's the negative of the gradient, or a vector that's perpendicular to a level curve, all those are ways of just asking for the gradient. All right. Yes. Yeah. The gradient is a vector whose direction is the max rate of change, and magnitude is direction of maximum rate of change, that points in the direction of maximum rate of change, and whose magnitude is the maximum rate of change. And you'll see that when you go to the worksheet, I'm basically going to be asking you the same questions, just in different ways, but they're all going to involve the gradient. Okay. So this next part I'm going to go through a little quicker because it's a function of 3 variables, but everything is still the same. To do the directional derivative, sorry that you should have a hat on it. To do the directional derivative, it's the gradient dotted with the unit vector in the direction of interest, same as in a function of 2 variables. And then just like before, it's going to give a vector. The gradient is a vector that points in the direction of maximum rate of change, whose magnitude is the maximum rate of change. So all the properties for a function of 2 variables hold for a function of 3 variables. Here's the one difference. For a function of 2 variables, as we saw here, I'll move this point around to some place where it's maybe a little more obvious. Let's put it right down there. There's a nice image. For a function of 2 variables, the gradient points in a direction that is perpendicular to a level curve. Well, remember, we talked about this when we talked about functions of 3 variables. They don't have level curves, they have level surfaces. So a normal vector actually points in the direction, is actually perpendicular to a level surface instead of a level curve. So it's not completely different. It's just that for functions of 2 variables, we have level curves. It's perpendicular to level curves. For functions of 3 variables, it's perpendicular to the level surface because we don't have level curves for a function of 3 variables. But again, it's what's so cool about the gradient, in my opinion, is this. It doesn't matter. It's very easy to use for functions of 2 variables, of 3 variables. It's easy to use for functions of 4 variables. All right. Now, here's a little exercise we're going to go through. I'm going to work through this one. So this is something from last time. We didn't do a tangent plane, so let's go ahead and do one now. And then we'll talk about what we're doing here. So if we wanted to find the tangent plane, if you remember what we need the partials evaluated at 1, 1 and the function evaluated at 1, 1. So first off, we're going to need f at 1, 1, which is 6 minus 1 minus 1. You guys can obviously double check my math on this one, guys, just in case I make any errors. We're going to need our 2 partials. Well, let's put them here. F sub x is easy on this one, negative 2x. F sub y is negative 2y. So f sub x at 1, 1 is negative 2. F sub y at 1, 1 is also negative 2. So to put together a tangent plane, just as a reminder, let me see, I bring up the notes from last time. So here's our formula for a tangent plane. Let's see, where's a good one? And I don't have it on any of that stuff, of course. So here's our formula for a tangent plane here at the bottom. It's f of AB plus f sub x at AB times x minus a plus f sub y at AB times y minus b. Guys, I've got all the information right there I need to find my tangent plane. If you can do partials, you can do a tangent plane. So 4 plus a negative 2, well, we'll fix that in the next one, times x minus a, so x minus 1, plus, once again, a negative 2 times y minus 1. And just so we don't have to deal with those plus negatives, z equals 4 minus 2 times x minus 1. Oops, didn't mean to do that, sorry. Plus negative 2 times y minus 1. And maybe we want to get it in this form here. So I'm going to do one more step of simplification. This is the tangent plane. So if you're asked for a tangent plane, this is fine for a final answer. But because of where we're heading with this, I'm going to distribute and then simplify. So we get z equals 4 minus 2x plus 2 minus 2y plus 2. And cleaning that up a little bit, we get 4. Actually, let's add all the constants together. We get 8 minus 2x minus 2y. Now, that's a tangent plane. It's actually not too bad, right? It's very similar to doing a tangent line in Calc 1. All right, now here's why we're doing this. Let's pretend that f is a level surface of a function of 3 variables. So what we do is we replace the f of xy with a z and then subtract the z over to the other side. That's where this minus z is coming from. So this is pretty cool. It's a cool little trick that sometimes is useful. So now we've got a function of 3 variables, but we're just going to be looking at one of its level surfaces, and we can look at any level surface we want. 6 minus x squared minus y squared minus z is the level surface for w equals 0, okay? So that is basically the same as our function. It's just now we're looking at it as a level surface. Well, we know that our gradient is perpendicular to our function w, its level surface, at the given point. So let's find our gradient of w. We'll find it as a general gradient first. So this is good. This would be a function for a function of 3 variables. It's going to have 3 components. So minus 2x, minus 2y, and negative 1. Okay, partial with respect to x is minus 2x, partial with respect to y is minus 2y, partial with respect to z is minus 1. Again, if you're feeling comfortable with partials, the gradient is no problem. Now, the only thing is we need the z value at the point 1, 1, because now we're a function of 3 variables. We actually already found that. It's just 4. So our normal vector is equal to the gradient of w at 1, 1, 4. So that's negative 2, negative 2, negative 1. Guys, this is a normal vector to our surface. Remember our point normal form of a plane. Negative 2 times x minus 1 minus 2 times y minus 1 minus 1 times z minus 4 equals 0. Now this is going back a few sections, but this is our point normal form of a plane. All right, now I'm going to distribute like I did up here. So minus 2x plus 2 minus 2y plus 2. You're probably already seeing the slopes are coming out the same. Minus z plus 4 equals 0. If I combine the constants, so 2 plus 2 plus 4 is 8, and I bring the z to the other side, I get minus 2x minus 2y plus 8 equals z. Same exact tangent plane we got before. Now, for a lot of what we're doing right now, Both of these are perfectly fine for finding a tangent plane. If you like finding a tangent plane the way I did it in black, you're fine. You're going to be fine. That's how we're going to do most of our tangent planes. It's very quick. But this is an alternative way of finding a tangent plane, is to think of it as a level surface. So basically you replace the f of xy with, the f of xy with a z, bring it over, then find your component, your three component vector, your three component gradient, evaluate it at the point that you want the tangent plane at, and then do your point normal form of a tangent plane. And again, right here, there's nothing wrong with having that as the form of your tangent plane. The only reason I multiplied it out is so that we could see that the two are equal to each other. All right. There will be times that the latter version is easier. There will be times that the former version is easier. And this will be brought up again way later this semester, this idea of turning a function of two variables into a level surface of three variables. But I just wanted to show you that one of the problems in the worksheet will ask you to do something like that. It's not hard, but I wanted you to be aware of what it's asking you to do. You turn the function of two variables into three variables by replacing this with a z. Take that z to the other side and you make it a level surface at 0. So really it's the same exact surface, but now we're thinking of it as a function of three variables. And so our gradient's going to have three components instead of two. All right. Questions at this point? Okay, then let's do this. I'm going to do the same groups that we did last time because I know we didn't get to the 13.4 worksheet, but here's what I want you to do today. I'm going to put I'll put the 13.5 worksheet in here and the 13.4 in case you don't already have it. But here's what I want you guys to do. I want you to work on 13.5 first, because that's what we just did. And it's the one that, I really want you to go through it because again, these problems hammer home the conceptual idea of the gradient, that it does give us the maximum rate of change. And I want you to leave in today with that tie being just so tight that every time you're asked to find the maximum rate of change of a function, you need to find the gradient. Okay. So I want you to start with the 13.5 worksheet. And then if you still have time, then go ahead and try the one on the 13.4 worksheet of finding the tangent plane. Both of these are going to be good practices on your partial derivatives and finding the gradient. You're going to be asked to find directional derivatives in a couple of cases. So remember, that's the gradient dotted with the unit vector in the direction of interest. And then you're going to be asked to find tangent planes, which is what we just did here. So let me also do this. I'm going to put this in chat. This is the link to this whiteboard so that way you can have access to it. That way you have access to the whiteboard, when you're in your groups, if you want to look back at any of the notes we did. Okay, let's go ahead and get you guys in groups so you can get started on this. And if you guys have questions in your groups, let me know. Guys, this is what we're going to spend the rest of the time on, is getting this down. Okay. Give me just a sec. It takes a little longer when I'm not doing it randomly. All right. Okay. and perfect. All right, guys, you should have the invite to the room. Sorry that took a little bit longer. You guys got the worksheet and you know what to do. Sorry, guys. I know you guys probably still working, but we're already at 6:25, so we're almost out of time, and I got to leave pretty close to on time today, unfortunately, for an appointment. And there's one thing I want to show you before we go. Now, first off, let me talk about the worksheets. Don't forget to upload your work, and remember to upload, the finished problem. So, if you didn't get to finish a problem today in your group during your group work, that's okay, because you have until Tuesday afternoon to upload it. So feel free to, finish it up and then upload it. Okay. Don't feel like just because you didn't finish it in your group, you don't get a chance to. You still have an opportunity because we do have limited time in here. All right. There's one other thing I wanted to show you. Two things, actually. First off, in case you weren't aware of this, I know we talked about it day one, but it's been a while. So I'm in our course in more, and I know a lot of times it's easy to get to things through the calendar, and I'll talk about this better explained here in a second. But if you go in through the course content folder, in course materials, under supplements, this is where you'll find detailed solutions, worked out solutions to the problems on the worksheets. So, if you're struggling on one, or when you go to study for the midterm and you're going over some worksheet problems, you do have access to the solutions outside of class. Okay. So if you weren't, if you didn't remember where those were, I just wanted to show you that. The other thing, when you go in through course content and you open up a module, so in 13.5, this is where you can find direct access to the textbook section if you want a little extra work there, or look and see what's going on in the textbook. Here's the worksheet, the PowerPoint, and then this is the other thing I wanted to talk to you about. I actually added the link to the calendar, and I'm going to start doing this when we do. This website, Better Explained, has a really intuitive way of explaining some of the things we're going to do in Calc 3. So I like to use it every once in a while. And so what I'll do is when those topics come up, I'm actually going to add it to the calendar to make it easier to find. But I wanted to let you know about its existence because, like with the gradient, again, the gradient procedurally is pretty easy. You take the partials, you plug in your point, you got your gradient. Conceptually, what's going on is what's really interesting because it is so powerful. Okay. So I like to use this site because they have some nice descriptions of the gradient, and especially when we get into line integrals and flux and some of that stuff. And don't worry, that's not until way later this semester. They do this intuitive approach and try and give, a real life example so you can get a better understanding of some of the topics we talk about in here because we have limited time together. Okay. So I'll make sure that those start going in the calendar as we move forward. But I wanted to just let you know, because I know people don't always go into the course content folder because you can get to the assignments and the lessons from the calendar. So I just wanted to let you know that all the stuff that I use is available in the course content folder. Okay. We only have a minute left. Any questions? Like I said, some of you guys have already uploaded your work for today, and that's awesome. And you can there's the problem or two groups had two problems. One group had one problem, but it was a longer problem. So y'all had about the same amount of work. So you had those from 13.5, and then you also have the 13.4 tangent plane problem. You guys upload that, and I'll be happy to give you credit for it. Again, those have to be up by Tuesday. And then we're going to be moving on in chapter 13 or module 3 next week. So use this weekend as a chance to really get the ideas of these past couple weeks down, because as you've noticed, everything really builds. All right. Maximum and minimums is going to involve partial derivatives. So our Lagrange multipliers. So make sure you go with your partial derivatives. We're going to be finding the gradient when we do maxes and mins. All right. So, and then obviously the chain rule has to do with derivatives. So the next three sections all have to do with partial derivatives. So this weekend, because it's our long break between classes, this is a good time to get caught up on the partial derivatives and really get that part down as we're moving forward. All right. Guys, I do have to leave today for an appointment, so I'm sorry I won't be able to take any questions. But if you do have questions, guys, you can always email me. Remember, you have access to the Math Center, tutoring through the Math Center. It does have hours on the weekend. You also have online tutoring through BrainFuse. You can email me, and you got the forum. I'll get the video from today and the whiteboards posted in more, so you have access to those. Sorry to cut out real quick today, but I do have to get going. But I will see you guys on Tuesday. And guys, if you do have questions, you know, like normally I hang around and answer questions. If you do have questions, shoot me an email and let me know. Okay. I'll get back to you tonight or tomorrow morning. No problem. All right. All right, guys. Great job today. Gradient. I mean, as you go through the went through the worksheet, hopefully you noticed, right? It was actually computationally, it's one of the easiest things we've done so far. And it's just so powerful. So I really enjoy this section. All right, guys, thank you very much. And I will see you guys on Tuesday. No problem, guys.